Thank you, Steve. Gosh, that's a hard introduction to follow. I guess I should just sit down and be done after that. Wow. So, as Steve said, my name is Michael Jennings. I work for Los Alamos National Laboratory. I'm the lead for the platforms team, which basically means my team and I are responsible for the system administration for all of our supercomputing resources. Everything from our Trinity leadership class machine on down. So Los Alamos, for those who aren't familiar, is a National Nuclear Security Administration laboratory. We're responsible, along with our peer labs, Lawrence Livermore and Sandia, for the ongoing certification of the U.S. nuclear stockpile. We also do a lot of other science in various areas, medicine, nanotechnology, alternative energies, and so forth. I always like to show this picture. You can see the canyon out there back behind my house, and you can follow all the way down out into the valley and up the mountains on the other side, completely unobstructed view. Really beautiful in northern New Mexico, and yes, we are hiring. So LANL's had a long history in high-performance computing. We were doing HPC before HPC was a thing. Ever since the 50s, we were the first of the national labs. We have a number of HPC systems throughout our history. Our current leadership class machine, you can see there in the bottom, is Trinity. It's 19,420 compute nodes, second largest cray in existence that we know of. It's got 2 petabytes of system RAM, 3.7 petabytes of parallel storage, burst buffer, 78 petabytes of parallel storage, and 3.3 terabytes per second of checkpoint bandwidth to the burst buffer. So it's a pretty nice system. So my talk today is called Container Mythbusters. What do I mean by that? Well, containers in the world of HPC technology are relatively new. As our last speaker mentioned, HPC has been around for a really long time. But containers are something that was not invented in HPC. For a really long time, HPC was the cutting edge of scientific and technical computing. In a lot of ways, we're not anymore. The hyperscale market has come in and done a lot of the innovation. And containers came primarily from the web app space. So from a certain perspective, we were kind of late to the game getting on board with containers. Those of us who found container technology early on tried to figure out how best to get it integrated into high-performance computing. But since then, there's been a lot of confusion, a lot of misinformation. Not everybody knows what containers are and how they work and how to properly leverage them for HPC. So I'm going to go through a number of different myths or misconceptions that I've heard along the way and try to teach you a little bit about what containers are and how we use them at Los Alamos. So the first one I always mention in all my container talks. Everybody thinks they know exactly what containers are, but you ask anybody in the industry and you're going to get a slightly different answer from every single person. There's a lot of different perspectives or definitions of what containers are. So that's always a good place to start. Let's get that out of the way first. What are containers? Well, it depends. A lot of people use container to refer to a file system image. Generally, when you run a container on Linux, that container runs with a particular file system image that's different from what the host has. And often that file system image is what we refer to as a container. More specifically, most container runtimes use a layered image with multiple layers, each layer being created by some step in the build process. And so that runtime is responsible then for merging or collapsing those layers into a single file system image. So a lot of times we refer to that as a container. In the Docker world, that entire set of layers of an image is referred to as a repository. Why? Because back in the early days, you could actually commit changes to an existing set of layers and create a new layer. And you could go, there's a Docker log command, you could go back and look at the change log. So it really was, in a sense, a repository in the vein of something like Git or Subversion or CVS. And then image is used in the Docker world to refer to a single one of those layers. But image, because of the way tags work in Docker and image layers work in Docker, each layer can only have exactly one parent. It can have as many children as it wants, but only one parent. So you cannot have multiple layers directly underneath any single layer. So by the time you get to the top of the stack, there's a unique path all the way down to the bottom layer. So whether you're referring to just that top layer or the whole stack, because there's end up being somewhat interchangeable, you can refer to either one a lot of times as an image. Container is also used to refer to the process that's running inside this file system or using this file system as its base. Typically, that's accepted as the correct definition of container. Containers are fundamentally processes, particularly when you look at it from the perspective of the kernel. A container is a process, and we'll get more into that later. Now, I like to think I use terminology correctly, but the reality is I'm not always consistent about what I call a container either. So if you get confused or if I say something wrong, definitely feel free to ask for clarification. Next myth, containers are the new truth. Anybody who's been in the Unix world long enough has lived through the challenges of truth. It's a privileged call for hopefully obvious reasons. And so daemons since the dawn of time for security have started themselves in chroot jails and used chroot to provide some level of security. You should also know that because of certain aspects of the POSIX standard, it's mandated by POSIX that there be a way to break out of a chroot jail. So people who rely on chroot for security are often sorely disappointed in the form of root exploits. So containers are the new truth. Well, no, not exactly. Containers use a number of different kernel features and system calls, the big one being namespaces. In the current Linux kernel, there are a total of 7 namespaces. One of them, the cgroup namespace, is relatively recent. Kernel 4.6 and above has the cgroup namespace, which basically gives you your own custom root of the cgroup file system. The other namespaces, there's a mount namespace, which gives you a customized view of file system mount points and mount options. The PID namespace, anything that starts its own PID namespace becomes process ID 1, and all of the things that come along with that, init semantics and so forth. The UTS namespace gives you your own host name and domain name. NIS is pretty well in the grave by now, so domain name doesn't much matter, but host name is pretty handy. The network namespace, you have your own devices, your own IP addresses, and so forth. Basically, your own view of the TCP/IP stack, IP tables, things like that. IPC namespace is shared memory, semaphores, and so forth. Now, all of those are considered privileged namespaces. You have to have a Linux kernel capability called capsysadmin in order to create any of those namespaces. There's one namespace that's unprivileged, meaning that any user on the system, assuming your kernel supports it, and you've, on Red Hat at least, you've turned that option on, you've raised the limit. You can create what's called a user namespace. A user namespace gives a process its own customized view of UID and GID mappings. Now, for privileged users, and in particular Docker, user namespaces generally work with ranges of UIDs and GIDs. So with Docker user namespace support, which is horrible, by the way, you have specific ranges of UIDs and GIDs that you map from the host into the container. Unprivileged user namespaces, on the other hand, work differently. You get one UID and one GID that get mapped into the user namespace, your real UID and GID on the host. Everything else gets mapped to essentially a nobody, a generic UID or GID. You can have whatever arbitrary UID and GID you want inside a user namespace if you're unprivileged. But outside that user namespace, you are whoever you are, and that separation is maintained within the kernel itself. And there are 3 system calls that do all of this work: unshare, clone, and setns. Brian Cantrell, if you remember him from the olden golden days of Sun, now at Joyent, I believe, he was the first person to refer to operating system virtualization or containers as lies. Containers are simply lies that we present to our applications. We give them a distorted, customized view of the system rather than the honest, actual host view of the system. In addition to the namespaces that I mentioned, there are other kernel features that are frequently used along with containers. C groups or control groups allow you to set kernel-enforced limitations on resource consumption for processes or for containers. This is often used by job schedulers like Slurm. Once upon a time, if you've been in HPC for a while, you remember the days where Torque and Moab, you would set a particular memory limit on a job, and the resource manager would have to sit there and poll, okay, how much RAM are you using now? How much RAM are you using now? How much RAM are you using now? Over and over and over again, and watch to see if any of the jobs exceeded their limit. And then if they did, it would then turn around and try to terminate that process or take whatever action you configured. That's no longer necessary thanks to C groups. You can set specific kernel-enforced limits on memory consumption, CPU consumption, bandwidth consumption, and so forth. All of that is controlled by control groups or C groups. And with the C group namespace, you can actually have your own fully managed subtree within the C group file system. SecComp or SecComp BPF is a Berkeley packet filter based system call filtering language. BPF was originally written to allow for fast packet matching on like a firewall. Well, it's essentially an in-memory language. You can compile C code that turns into byte codes in memory that are very, very, very fast to execute. It's now I believe, a Turing-complete language within the kernel that's being used for all sorts of stuff like performance testing. But seccomp in particular allows you to set which system calls are or are not allowed and what actions to take if certain system calls are detected. Docker, for example, uses this to prevent contained processes from doing things that no container should ever do. Things like removing kernel modules, adding kernel modules, and so forth. So you can use a BPF program with seccomp to terminate a program if it tries to do certain things that containers should never do. And if you're careful about it, you can, and I've done this with SSH, you can go through and enumerate every single system call that SSH should ever actually do in the normal course of running, disallow all the others, and the moment there's an exploit on your system that tries to load a rootkit kernel module into the kernel, boom, gone. So containers use that to protect the system from potentially compromised or malicious containers. PRCuddle, there's a flag called no new privs that you can set, which essentially tells the kernel, don't ever give this process or any of its children any additional privileges. So execve, no matter what flags or capabilities are set on the file system, will never ever grant privileges to that process or any of its child processes ever under any circumstance. That flag, once it's set, you can never unset it, and it's maintained by the kernel. This flag is used to ensure that once a contained process gets launched, nothing inside of that container, inside of that process or any of its children can ever gain privileges. So nothing can be set UID root and become root, or pass credentials along a Unix socket to get root, or anything like that. Privileged containerization, meaning a set UID executable or a root-owned process like the Docker daemon that spawns containers, that is not safe unless you can use no new privs. SE Linux is a mandatory labeling system or mandatory access control system for the kernel, where you define specific policies for files and processes on the system. What are they allowed to do? And anything that's not explicitly allowed is denied. SE Linux is very important for containers to make operations within the container confined to the container space so they can't overstep their authority. AppArmor is a similar but different system, primarily used on the Debian and Ubuntu and offshoots of those. It's similar to SE Linux. The way you set up AppArmor profiles is a lot friendlier than SE Linux, but you don't get the file system labeling or capability stuff with AppArmor. Next myth, and this is actually kind of a twofer. When we first started looking at containers, a lot of people thought of containers as analogs for VMs. Containers are lightweight VMs, so I'm going to take this server over here and I'm going to turn it into a container, and I'm going to run it as a container instead. So I'm going to replace all of these big bare metal servers with a bunch of containers. So yeah, you can do that, but just because you can doesn't mean you should. Containers, and in particular I'm talking about the Docker and OCI ecosystem of containers. When we say containers in that context, it's really short for application containers or app containers. Application containers are not analogs to systems, they're analogs to applications. Those of us who've been in the industry for a while, do you remember char files? Anybody remember char files? A char is basically a self-extracting tarball. It's a shell script that has a tarball tacked on the end of it. Containers are kind of like that. In fact, the Willy Wonka of containers, Jesse Frizzell, wrote a tool called BinCutter, B-I-N-C-T-R, which is still on GitHub if you're interested in checking it out. Brilliant piece of software. She actually takes Docker containers and builds a Go program that tacks the container in base64 form onto the Go executable itself. So it's a modern version of char files, but it's a launcher for the container that gets attached to it. So you can turn, say, the Nginx Docker container into an Nginx executable on your system, which will launch inside that container. Cool stuff. So application containers are a way of coupling the environment that you want an application or a process to run in with that application itself. It can be as much as a full operating system. You can limit it to just the libraries and support files that the application needs, and so forth. The term operating system virtualization, a lot of times people will get that confused because they think of hardware virtualization. All that really means is that we're giving the containerized application a different view of the underlying file system structure. That may be because we want to run it in Ubuntu on a host that's running Red Hat Enterprise, for example. Or it may simply be that we want to present it with a read-only file system instead of something that's writable for security. So containers allow us to play tricks like that with our applications. But again, from the perspective of the Linux kernel, a container is always just a process. There are container runtimes, Docker being the big one, that allow you to create virtual networks and different things within the namespaces that the container has access to. In the world of unprivileged runtimes, like our Charlie Cloud, network namespaces are largely useless because all you get access to is a single loopback interface, and all of the stuff that Docker does behind the scenes to present the network to a container requires privilege. So none of that stuff is there in those runtimes. Now, again, I'm talking specifically about Docker and the OCI ecosystem and the application containers. There are other container solutions that work differently. There's something called systemd nspawn. Systemd wants to control everything. Containers are no different. So they have their own container system called nspawn, which basically expects to boot a container. So you have an entire root file system image, and you tell systemd nspawn to boot it as if it were kind of like a miniature VM or host operating system. There's a product called LXD that Stefan Graeber from SUSE put together that offers a lot of vSphere, VM cloud-like features. You can do live migration, you can do snapshotting and things like that. There's a lot to it. That, again, is targeted more at the replacing hardware, virtualized hardware with containers market. And even in Docker, you can tar up, and I have done this, admittedly, you can tar up the root file system of an existing server, import it into Docker as a container, and run it as a container. But if that's your goal, there are probably better ways of doing that. You always use the right tool for the right job. And when we're talking about specifically high-performance computing, HPC job containers are application containers. Microservices, which is the other side of HPC containering, are not generally application containers. They're microservices containers, and those can be done a little bit differently. So this is a fun one. If any of you have ever heard Dan Walsh, Red Hat's SE Linux expert, if you've ever heard him speak, he's a brilliant guy, very, very fond of saying, containers don't contain. And I was thinking about this, and he's right, but not entirely right. So what's the fact? Containers do contain, but it's a passive action, not an active action. A lot of times from the security standpoint, if we have this expectation for containers to contain, we're thinking of prison, we're thinking of jail. We want to confine these processes inside of something. And that's not the way it works. In fact, the kernel specifically supports mechanisms for processes to move between different namespaces. So namespaces fundamentally are not intended to jail or contain. They're more like buckets. Containers are ways of grouping stuff together. So if you think of it more as a bucket or a Ziploc bag or some Tupperware, that's more how containers contain. They group things together, like the root file system that we've virtualized, or a set of processes that one of them needs to be an init-like manager for the others. So containers do contain, but they don't imprison. They just group stuff. Unprivileged containers have a distinct advantage in that there are very specific, very well thought out and well-defined rules governing that very first thing I mentioned, moving in between namespaces. An unprivileged container does not have free rein to join any namespace it wants anywhere on the system. It has to have certain ownerships and capabilities, and those policies are directly enforced by the kernel. So it's very safe to have unprivileged containers in that context because the kernel prevents them from doing anything that they shouldn't be allowed to do. A lot of testing, a lot of research and development, particularly by Eric Biederman at Google, has gone into making user namespaces as functional yet as safe and secure as possible. No matter what you use, you're trusting something on your system, if you're running containers, to manage the privilege boundary between those containers and the rest of the system. With user namespaces, that thing you're trusting is the kernel, the thing you're already trusting. If your kernel has an issue, all bets are off. If you're running a privileged container engine, such as Docker or Singularity, you're trusting that piece of software to manage the privilege boundary rather than your kernel. So I don't know who remembers the Hertz rental car commercials from, what was it, the 90s, I think, but it's true with containers as well. There's secure and there's not exactly. So make sure you choose the right one. So I hear this all the time. Containers are just another way of saying Docker containers. Well, no. Containers can refer to a lot of different technologies, and there are a lot of different parts and pieces in the overall container landscape. So Docker was not the original container implementation. You may have heard of LXC, which was Linux containers. Before that, there were a few, I don't want to say false starts, because that's really not fair, but there were other attempts to do similar things in the kernel space. There was something called Linux vServer, OpenVZ. These were attempts to patch the kernel to do very similar container-like things, basically fix the problems with chroot that we couldn't fix because the POSIX standard mandated it. Well, finally, with LXC and with kernel namespaces, we can do those types of things now where we couldn't before. What Docker really did was made it easy to produce containers, share containers, distribute containers, and maintain containers. It was very easy, very well defined, and that's really why Docker took off. Now, they kind of made a mistake. They, I guess, got too comfortable with their success, and there was some really constructive feedback that the community was trying to give to Docker in terms of security, particularly around the way they stored container repository images. And they didn't want to change their format. So there was a paper put out and a project came out called Rocket and the AppC spec that had added features around non-repudiable signatures and content addressable storage for security reasons. Because of that sudden bifurcation of the container community, a bunch of container users like Google got together and created the Open Containers Initiative as a Linux Foundation project to try and avoid splitting the container community permanently and get everybody back playing in the same playground again. So Docker decided to play along and contributed their own container runtime and daemon stuff as the initial version of the OCI runtime and image spec. And now those are maintained by the Open Containers Initiative with members from different companies within the community. For HPC runtimes, NERSC's Shifter was the first one that came along. They are the ones who pioneered the single file parallel storage method of launching containers. If you use a parallel file system to distribute a single file that contains all of your container stuff in it, you get a huge win in terms of startup speed because you reduce the metadata queries to your MDS, and instead all of that stuff can be cached locally on each individual compute node. And so Shifter sets up an image gateway that pulls the container down from Docker Hub and turns it into a squashfs file system on your parallel storage. Then when the user's job runs, it launches inside of that squashfs image. You also get the security benefit of the conversion of that Docker container layers into a file system image. Having that process not be controlled by the user is extremely important for security. There have been multiple security vulnerabilities in the kernel in the file system drivers because historically there was no way for anybody other than root to present a raw file system image to the kernel. Now all of a sudden, between privileged namespaces and other things, we have non-root users presenting raw file systems like ext3 directly to the kernel. And there have been potential opportunities for corrupt file system images or malicious file system images to then become root compromises on your system by leveraging container runtimes and such. Shifter's image gateway and the way they do the image conversion prevents that from happening because it's a system managed process, not a user controlled process. Charlie Cloud, which is Los Alamos's container runtime, went in the other direction. Ours leverages user namespaces for a completely unprivileged operation. That means that any user can install and use Charlie Cloud without having to have root access. They don't even need us as administrators to do anything at all. And all of the actions that that user takes are controlled by the kernel. So we don't have to be in the business of worrying about root exploits or anything like that. It's all maintained by the kernel. And the way you get your container image out to the different compute nodes is entirely up to the user. You can have a directory on parallel storage. You can have a squashfs file system on parallel storage. You can use sbcast with Slurm to distribute the file system image. However you want to do it, Charlie Cloud doesn't care, as long as in the end there's a directory structure representing a root file system on each of the nodes. Singularity started its life as a non-container container that was based on chroot. And a bunch of old technologies put together that weren't really well understood how it was working under the hood, and caused a lot of confusion and grief. And very, very quickly, like within a couple of months, after 1.0, 2.0 came out, which was a complete rewrite and was based around containers and namespaces and things like that. There's also a new player that's starting to get some attention in HPC called Podman. I mentioned Dan Walsh earlier. His team at Red Hat developed this thing called Podman. It's a drop-in, and I mean that literally, a drop-in replacement for Docker. You can alias Docker equal Podman, and all the commands you're used to using with Docker will just work. The difference is there's no root daemon, so it works directly as you, or if you're root, it works as root, but with no daemon. And you can run unprivileged containers now with Podman. So this is something that we're looking at as well. Next myth, containers are hard and they require complicated software. So a lot of times that's true. You want something like Docker that's robust and featureful. But containers, the very basics of containers are actually pretty simple. There's only 3 system calls with a few flags. And if you have a modern distribution of Linux, there's a couple commands that come with it, one in particular called unshare. You can actually write your own container implementations in bash shell scripts. And we are actually doing this today. We had a particular service that wanted to run some arbitrary commands on our systems for auditing purposes. Obviously, that's something that could very easily be abused in the wrong hands. So we put together a really quick, customized container implementation that essentially unmounts all of the unnecessary file systems, things like Luster, that you don't want something walking the file system tree. That'd be really bad. It unmounts all of the other file systems. It mounts the root file system as read-only. And there's a very narrow directory tree that it has write access to, but everything else is either unmounted or made read-only. And so it provides the information that process needs to be able to do its job, but protects the system from any compromise or even just editing of the file system or changes to the file system. So there's a lot that you can do that's actually pretty simple. What's difficult is all of the gory details of implementing your own runtime and doing it safely and securely. That's where the challenges are. But just doing containers is actually really straightforward. This might be my favorite myth. Docker is insecure. I've heard this probably more than anything else. And yeah, okay, the security record for Docker is not great. There have been depending on how you count, at least 17 vulnerabilities since early 2017. And they only got 2 CVE identifiers from MITRE for all of those vulnerabilities. There was one particular release that fixed a total of 6 vulnerabilities all at once. And one of those CVEs covered multiple vulnerabilities, including one where you could join and manipulate the host namespace. You could test for arbitrary files existing or not existing with root privileges. And you could escalate to root by replacing the contents of user bin. And 7 out of 9 of the releases that were made in 2018 were releases for security vulnerabilities. There was recently an audit done. I won't read you the quotes, but you can read them up there. One in particular about the set UID binaries being difficult and complicated. I have a little confession to make. That's actually not Docker. That's Singularity. So now let's move on from the good facts to the real facts. Docker is actually pretty secure. When you hear people refer to vulnerabilities in Docker, that's usually a result of what I call pilot error. Docker restricts access to the Docker API for a reason. It was designed to only be accessed by root. Now, there are mechanisms if you need to expose the Docker API to other users. Docker Enterprise offers an authorization plugin where you can do things like that. But the community edition of Docker is designed and implemented specifically to offer services to the root user. So if you open up access to the Docker API to other users, that's a decision that you're making. So technically there were 5 CVEs that came out for Docker since early 2016. I picked that year because that's when all 3 of the HPC runtimes were available and had passed their initial, let's say, burn-in stages. So since then, there have been 5 CVEs that have come out against the Docker engine. But again, unless you are opening up access, there's no way for privilege escalation to occur because you have to be root in the first place. So the only real context where you could have a vulnerability in Docker is if Docker allows you to create a compromised container that some unsuspecting person might download and execute, and that malicious container then compromises the overall system. So depending on how you count, 0 or we'll say up to 5 vulnerabilities in Docker over the past few years. Charlie Cloud, 0. Shifter, 0. Singularity, at least 17, although only 2 have CVE identifiers, but 17 separate vulnerabilities, some of which comprise more than one actual underlying vulnerability. So 17 or more, depending on how you count. And today we have lots of different options for how to do this. I mentioned Podman. Podman's getting more uptake. User namespaces, I'll talk a little bit more about that here shortly. And all of the mainstream HPC Linux platforms, RHEL and SLES both now support user namespaces basically out of the box. For RHEL 7, there's a limit that you have to bump up, but you can do that at runtime. SLES supports it out of the box with no limits. So again, if you open up access to your Docker daemon, it's not the security vulnerability, you are, and you've made that decision. Next myth. Containers solve the problems of reproducibility in science. Not exactly. Reproducibility is a really hard problem, and depending on what exactly you mean by reproducible, it can be a really, really hard problem. Typically, when people say reproducible or reproducibility, what they really mean is prescriptive. Docker and the Docker file format are great for sharing with other people, how did I generate the container that I ran in? How did I get from base CentOS or base Ubuntu to the point where I could run my science and get my results? Docker files are great for that because they make it easy to share with other people how you did what you did. But if you wait 5 years or even 1 year and you regenerate that container with that exact same Docker file, the chances of you getting the exact same contents or even similar content very quickly diminish. Because as I mentioned down here, yum install some package, that's not always going to get you the same results. Packages get updated all the time. Distributions rev all the time. And some people, when they say reproducible, they mean bit for bit the exact same container image that you originally had. And with things like timestamps and such in the tar format that containers use, that's incredibly difficult to achieve. So there are research projects trying to solve this problem. None of the existing container runtimes, certainly, none of the existing solutions even have really tackled this problem. What we can do is preserve the artifacts. When you build a Docker image, that top layer has a particular hash value. If you preserve that hash value and that layer stays in, let's say, Docker Hub for a long time, somebody can go and fetch that specific hash, and then they will get the exact container that you ran in. But for onesie twosies, that's doable. If we wanted to preserve every artifact of every container build for every piece of science that gets done from now until doomsday, that's a really big Docker hub that we would need. So we're looking for better ways to solve this problem, but it's not a solved problem yet. Containers are secure as long as the UID you have inside the container is the UID you have outside the container. I can't count the number of times I have heard this. Raise your hand if you've heard somebody say that to you before. You're the same UID inside the container as outside the container. Container security is complex and nuanced. There's a lot of subtlety to it. So if somebody says that to you, either they don't understand those nuances, or they do, they're assuming you don't, and probably trying to sell you something. The example I like to use is bash. If you install bash set UID root and set GID root on your system, and you run bash, your UID and GID will be the same inside the bash as they were outside the bash. Does that make it safe? Or if I told you that was perfectly safe to do, would you think I was crazy? Hopefully the latter, because there's a lot of stuff that goes on between when you type bash and when you get your bash prompt that create opportunities for things to go wrong. So what's important, what matters in terms of security is all of the stuff that happens in between. And if you use an unprivileged runtime, all of that stuff that happens is in the hands of the kernel, which you're already trusting, and which all of the people who developed the user namespaces and such in the first place put a lot of effort into getting right. And they're the people who know best how to get it right. If you're using a privileged runtime, then you're trusting those same kernel developers and the same kernel, plus the developers of your additional software. And as we saw a few slides ago, they're not always as secure as they like to sell you they are. Exposing privileged operations to unprivileged users, which fundamentally is what containers do, requires deep, deep expertise, deep understanding of kernels and how all of those things fit together. Last one, user namespaces are too new to be considered secure. I hear a lot people saying, well, user namespaces are so new, they're brand new, not everybody supports them. Sure, that was true 5, 6, 7 years ago. It's not true today. So user namespaces have been around for quite some time. The initial implementation was in 2013, and they've remained substantially unchanged since 2015 in kernel 3.19. Now, I'll be the first to admit there were some pretty unfortunate corner cases in the early days with user namespaces. There were some things that happened that didn't get caught right away. But for the most part, those things have been worked through. And user namespaces, as I mentioned, are supported on the major platforms. Even if we had a system, which we do, that the kernel doesn't support user namespaces, I would still not run a privileged container runtime. I would say, sorry, we can't run containers on that system quite yet. We need to upgrade it, or we need to get a new system. It's simply not safe. Most there was yesterday was mentioned the new Runcie vulnerability. Basically, Runcie was allowing a malicious container to be set up such that once root invoked the container, it would compromise the originating binary. Basically, a malicious container could overwrite Runcie on the host system. So properly configured user namespaces as well as properly configured SE Linux both prevent that vulnerability completely. So with, for example, Charlie Cloud, you can still run untrusted containers and you don't have to worry about that vulnerability. So I mentioned Charlie Cloud a few times. It is LANL's container project. We now have a few students who are working on development with us along with the main developers. We won an R&D 100 award last year, which was pretty awesome. Those of you who aren't in the national lab circuit, these are like the Oscars for us, the R&D 100 awards. Reed just did a new release earlier this week of 097. One of the big things we've been working on over the past few months is really cleaning up the documentation and making as many examples and tutorials and so forth as we can, and making them as simple as we can. So the documentation quality has really, really gone up. I encourage you to check it out. If you use containers at all in an HPC context, it's by far the safest way, in our opinion, to do it. So that's it. Hopefully I've at least made you think and answered a few questions you may have had along the way. Are there any questions?
So, performance-wise, so I'm using the bare metal, and tomorrow I'm going to use any of the containers. Are there also differences in performance?
Generally speaking, the container runtime itself, whether it's Shifter or Charlie Cloud or Singularity, none of them is going to substantially impact the performance. Where the differences in performance tend to come from is how they handle the underlying image.
Can you elaborate more on that?
So Shifter, as I said, was the first to distribute a single file system image using SquashFS. Because that's a single file on the parallel storage, there's a single metadata query to the MDS to get the information for that one file. Whereas if you launched like a Python script with a bunch of dependencies, if you launch that against a directory tree on your Lustre file system, it'll pound the crap out of your MDS at scale, and you're going to have a bad day. So how the file system image gets distributed has a lot more impact on the performance than the container runtime. Once the container runtime, whichever one it is, once it sets up the namespace stuff, it gets out of the way. Everything else is the application and how the data for the container gets to the nodes.
My second question, if I may, okay, the ideal target for containers would be that I don't care what kind of hardware I have, x86, Power 9, or ARM. Is that true? Would that be a myth?
So containers can't virtualize because the kernel is shared. So there's no way to abstract out different hardware in the context of a container. What containers do by you, and what we and Livermore, particularly the SPAC project you heard Todd yesterday, what we're working on is having SPAC not only build the containers for us to distribute, but we also want SPAC and other tools to instrument those containers with metadata around the compiler flags and such that were used, so that we can build optimized containers for Trinity based on Trinity's exact hardware, an optimized container for Sierra, an optimized container for Titan, and so forth. And we then want to hide from the user the details about exactly how all of that happens and what's on the inside, and just allow a user to submit a job to the exascale platform, the exascale universe, and have it go to the right place with the right container on the right hardware and just work optimally.
I'm sorry, I do have a third question. Let's suppose I'm doing high-resolution imaging recognition, and I'm using Fortran.
Mm-hmm.
And I happen to have multiple compilers for Fortran. How would I approach for my code to run in multiple machines which are dramatically different from ARM x86, Power 9?
So the big thing is the communications protocol. As long as the communications protocol, whether that's MPI or gRPC or whatever you choose to use, as long as that wire protocol is hardware agnostic, so there's a defined endianness to it and so forth, it shouldn't and doesn't matter what the processors are. For example, Trinity is part Knight's Landing and part Haswell. And we have run jobs across the entire machine, having both halves communicate with each other, even though they are different architectures. We can build optimized code on one that won't run on the other and vice versa. So fundamentally, it's all about the communication as far as compatibility between different types of hardware.
Thank you.
Yes? Go ahead.
I was wondering, so can you share what large agency centers or whatever have been adopting Charlie Cloud? What kind of is it making those decisions? Do you have that information?
I can say a number of them are looking at it. Part of our problem is we're shy and we have day jobs. So we are not out evangelizing and promoting Charlie Cloud to other places. Neither are the shifter guys. But right after that slew of security vulnerabilities initially hit, there were several within a span of a few weeks, as I recall. I got a number of calls and emails from people going, what the hell's going on with this? We're tired of this with Singularity. Can you help us with Charlie Cloud? So that was definitely a catalyst for getting people to start looking at Charlie Cloud and other Podman and other unprivileged runtimes. As far as who, I know all of the major national labs have looked at it. I've talked with people at Red Hat about it, and we've got a ongoing conversation with them. I'm starting to engage with the SUSE folks, talking about it. The quotes that I showed on the security page about the set UID binaries and everything, those quotes were Matthias Gersner from SUSE when he did an audit of Singularity, whether or not to include it in their distribution. He said, okay, I guess after we fix all the stuff and do some additional hardening, we can include it, as long as no users who aren't in the Singularity group can run the program. He didn't want to open it up. He didn't feel safe. So given that analysis, we're trying to get Charlie Cloud in front of the right people to give them an alternative. You know, it's not going to be right for everybody, but it certainly is going to be a lot lower maintenance than the alternative. One last question? Yes, yeah.
That bulk memory that they're talking about, that they're going to be selling someday, has that factored into how Docker would work as far as, because it's also directly addressable besides being sort of highly addressable?
So we have a similar challenge on Trinity. The Knight's Landing nodes, as you know, have high bandwidth MCD RAM on the processors, and figuring out how to best make use of those has been part of the challenge of getting Trinity working successfully. What containers allow us to do potentially is abstract away, as I mentioned before, the details of how that hardware is being leveraged, and just allow the users to focus more on coding the code. And we can handle making sure that the software, us and SPAC has a lot to do with it as well, but making sure that the code is built and optimized properly for whatever platform they end up running on.
The other question was about version control. Is that going to be incorporated in your software so that if somebody pulls up an application, all the versions of all the subsidiaries can be pulled in as well, that the correct versions of that application and operating system, operating environment as well?
So we feel that version management of the application, and by extension, the containerized application, is orthogonal to the maintenance of the runtime. There are great ways to maintain versioned containers using Dockerfile and Git, for example. But that's not something that we would step into. All of our code teams already have a long history of how they maintain their applications and their code, and the interactions of their code with the Cray programming environment, and that is already complicated enough without adding any additional complexity. So having something that just integrates seamlessly into what they're already doing, the way Charlie Cloud does, simplifies things for our code teams rather than making it more complicated and giving them more maintenance headaches.